You ever wonder how a plagiarism detector can sniff out one copied sentence in a 1,000-page book? Or how DNA sequencing finds crucial genetic markers? Well, at the heart of it all is a classic computer science problem, finding the longest common substring. And today, we're going to tear it apart and show you exactly how it works.
It's kind of wild when you think about it. These incredibly different technologies, plagiarism checkers, bioinformatics, even the diff tool programmers use to compare code, they all boil down to the exact same fundamental challenge. They're all just looking for the longest identical piece of text shared between two sources. So let's pull back the curtain and see the magic.
All right, first things first. Before we jump into solutions, we need to be absolutely crystal clear on what problem we're actually solving. Getting the definition right is everything.
The definition sounds simple, but there is one key word here that changes everything: contiguous. This is the whole ballgame. We're looking for a block of characters that appears in both strings. And this is the key: those characters have to be neighbors. No gaps, no interruptions, just a solid, unbroken chain.
And this right here, this is the #1 trap people fall into, especially in interviews. A substring is not a subsequence. A substring is a solid block. Think CDE from ABCDE. A subsequence, on the other hand, can have gaps. You could pull ace out of that same string. That's a subsequence. For this problem, we only care about substrings. No gaps allowed.
Okay, so how do we find this thing? Let's start with the classic approach, the one that's super intuitive because you can literally draw it out. It's often called the grid method, and it's a perfect example of a powerful technique called dynamic programming, or DP for short.
Seriously, just picture this. We take our two strings and lay them out on the top and side of a grid, kind of like a spreadsheet. The answer we're looking for, the length of the longest common substring, is now just a number hiding somewhere inside that grid. Our job is to fill in the squares and find it. So let's walk through this. We go cell by cell. Look where the C from the side and the C from the top meet. The characters match, so we start a count and we put a 1. Now move to the next diagonal cell. D and D. They match too. So what do? We look at the cell diagonally up and to the left, which has a 1, and we add 1 to it, giving us 2. The streak continues with E, giving us 3. But the moment the characters don't match, like E and M, boom, the streak is broken. We reset back to 0.
The real beauty of this whole thing is how simple the rules are. For every single cell in that grid, you just ask 2 questions. Do the characters for this row and column match? If yes, look at the top left diagonal cell and add 1. If no, just write a 0. That's it. That's the entire algorithm.
Now, for those of you who speak code, this is what that logic looks like written down formally. This is called a recurrence relation. Don't let it look intimidating. It's just a super compact way of saying exactly what we just described. If the characters are equal, the value of our cell is 1 plus the diagonal. Otherwise, it's 0. Simple as that.
So once the entire grid is filled up, finding the answer is the easiest part. You literally just scan the whole grid and find the biggest number in there. That's it. That's your answer. In our example, the biggest number is 3, which corresponds to our substring, CDE. Okay, the grid method is fantastic. It's clear, it's correct, and it's what you'd probably code in an interview. But it has a catch. Its speed is tied to the size of that grid. If you have 2 strings that are 1,000,000 characters long, you're looking at 1,000,000,000,000 calculations. That's way too slow for the real world. So we need something faster. Let's look at the pro solution.
I mean, just imagine trying to compare 2 human genomes. You're talking about billions of characters. That DP grid would be astronomically huge. It would take ages to compute. For problems on that scale, we need a totally different way of thinking. We need something that runs in linear time.
The secret to that incredible speed is a very clever data structure. It's called a suffix automaton. Now, yeah, the name sounds pretty intense, I'll give you that. But the core idea behind it is actually beautiful. We're not going to get lost in the weeds of how to build one, but we are going to understand why it's so fast.
So here's the genius of it. Instead of a grid, you first take just one of the strings and you build a special kind of map from it. That's the suffix automaton. Think of it like a super optimized search index for every single substring inside that first string. Then you just take your second string and trace it through the map, 1 character at a time. The longest you can go before hitting a dead end, well, that's your longest common substring. It completely avoids the grid and gives you that insane linear speed.
So now we've got 2 tools in our belt, the simple, intuitive DP grid and the blazing fast suffix automaton. So which one do you reach for? Well, like with everything in engineering, the answer is, it depends. It's all about the trade-offs. Let's break it down.
For a coding interview, the DP grid is your best friend. It's easy to explain, it's straightforward to code on a whiteboard, and you can show off a little by talking about how to optimize its memory usage. The suffix automaton, on the other hand, is the industrial strength solution. You use that when you're in a production environment working with massive data sets where every millisecond of performance counts.
All right, let's bring it all home. Time for the cheat sheet. If you're walking into a tech interview tomorrow, these are the absolute must-know points to have ready to go.
Here's your game plan. Step 1. The second you hear the problem, clarify. Ask, just to confirm, by substring you mean a contiguous sequence, right? That shows you know the key detail. Step 2. Lay out the DP grid solution. Explain the logic clearly. Step 3. Mention the space optimization. Say, and of course, we can optimize the space down by only keeping the previous row of the grid. Step 4. The bonus round. Name drop the suffix automaton as the best possible solution for huge inputs. And finally, always think about edge cases. What happens if one or both strings are empty?
So we've totally nailed how to find the length of the longest common substring. But here's something to think about on your own. What if there's a tie? What if there are multiple substrings that all have that same maximum length? How would you change our grid method to not just find the length, but to actually find and return all of them? Think about that for a bit, and you'll be well on your way to true mastery.